So in section 9 we'll talk about discrete time Fourier frequency analysis. We'll start by introducing the discrete time Fourier transform, which is discrete in time as you can see, but it is still continuous in the variable frequency, so not very useful. We'll also obtain a transform now that is discrete in frequency, so it will be discrete in time and frequency. It's called the Discrete Fourier Transform, or DFT. We'll make a little summary about all the Fourier series and transforms that we've encountered in this course. We'll introduce the fast Fourier transform, which is not a transform but an algorithm. We'll skip the section about the implementations of the algorithm itself, and then we'll talk a little bit about Matlab and Python. Well, this is a slide that we have introduced at the end of section 8, and now we intend to fill in the blank that you have here at the bottom right. Remember that you can obtain the Fourier transform from the Laplace transform simply by replacing S by j omega. Of course, this can only be done if sigma is equal to 0, which is the j omega axis, is in the region of convergence. We've also seen, and this was the main topic of section 8, that if you take the Laplace transform of a sampled signal, t is equal to kts, you obtain the z transform. Here both the Laplace transform and the z transform are the two-sided transforms, and there is also a one-sided transform where the minus infinity in the sum and integration is replaced by a 0. The relation between the z and s parameters is z is the exponential of tss. Well, the blank at the bottom right of the slide can be filled in quite easily. What we'll do is, of course, sample the signal at t is equal to kts, and if you inject t is equal to kts in here, well, the integral will become a sum. We'll have f of kts, and as we have done previously, well, we won't write this ts all the time, and we'll simply write f of k. Of course, you have to remember that in the background there is this sampling period ts, and if you replace it in here, you can write this exponential of minus j omega t as the exponential of minus j capital omega k, where omega is this capital omega here. The discrete frequency is written as a function of the analog frequency times ts. Remember that this one is in radians per second, right? ts, of course, is in seconds, so the discrete frequency is simply expressed in radians. So this is the discrete time, for obvious reasons, Fourier transform. Okay, so you can obtain it from the Fourier transform by sampling, but you can also see that you can obtain it from the z transform, right, by replacing z by the exponential of j times the discrete frequency. Okay, and just like you can obtain the Fourier transform from the Laplace transform, it's true in most cases. But what you have to have is sigma is equal to 0 in the region of convergence. Well, obviously, sigma is equal to 0. The j omega axis will transform into the unit circle using this relation. So it's kind of obvious that this way of obtaining the discrete time Fourier transform and simply replacing z by this expression is valid only if z is equal to 1, the unit circle is in the region of convergence of the z transform. Okay, this omega over here, this capital omega, well, it can be obtained from this relation over here. S as sigma plus j omega, right? So this one you can write as E t as sigma e to the j omega t s, and this is here omega and this is r. Okay, so you can see indeed that this is the discrete frequency that we have been introducing in section 8, and you can see here that you can go from the Z transform to the discrete time Fourier transform by simply writing this equation, and r is equal to 1 has to be in the region of convergence. R is equal to 1 is of course the unit circle. So this is how we obtain the discrete time Fourier transform. It's, well, it can be written like this, so please don't learn this by heart and obtain it from the Fourier transform simply by sampling. The variable capital omega is the discrete frequency. It's expressed in radians, and of course it's a continuous variable. So this is why this discrete time Fourier transform will not be that interesting, because, well, it's difficult to work with it and it cannot be implemented on a processor because, well, the discrete frequency is still continuous. We've seen in the previous section that when you sample, everything becomes periodic, and what is usually done is, of course, to consider this discrete time Fourier transform over one period, and usually it's the period from -pi to pi. There is also an inverse transform over here, but this is not that important. We have seen that the discrete time Fourier transform is linked with the Z transform. We had something similar for the, well, classical Fourier transform. It is the Laplace transform with S replaced by j omega. Of course, we assume here that j omega is in the region, j omega axis is in the region of convergence. So the j omega axis is sigma s equal to 0, must be in the region of convergence. Okay, if this is the case, it's the easiest way to obtain the Fourier transform. You take the Laplace transform and you replace s by j omega. Laplace transforms are quantities that you know very well. Well, if you have a sequence f of k, you can do the same trick. Okay, obtain the discrete time Fourier transform. Well, you start from the Z transform and you replace by Z is the exponential of j times the discrete frequency. Okay, so this means here that r is equal to 1. Okay, remember that here s is sigma plus j omega. Okay, if in order to write this, sigma is equal to 0 must be in the region convergence. Here z is r e to the j omega. So in order to write this, r is equal to 1, so the modulus of z is equal to 1 is in the region of convergence. If this is the case, this is a simple way to obtain the discrete time Fourier transform. This should not be a surprise, because by this relation over here, the link between the z domain and the s domain, the j omega axis, well, is mapped to the unit circle. We have seen that in the Laplace domain we can always use this trick for functions f of t of finite support, because if a function f of t has finite support, its Laplace transform f of s will have a region of convergence that is the whole s-plane. We'll have something similar for discrete time signals f of k of finite support. Its Z transform will have a region of convergence that is the whole z-plane. You might have to exclude the origin or infinity, but at least it will contain the unit circle. Okay, so for signals of finite support, discrete time signals of finite support, Obtaining the discrete time Fourier transform is easy. You take just the z transform and you replace z by this expression. We have seen that when a signal is sampled, everything becomes periodic in the frequency domain. This is something that we have discovered in the section dedicated to sampling theory. So this DTFT, this discrete time Fourier transform, we'll consider it. It will become periodic of period 2 pi, so we'll consider it in the range minus pi pi, but this is equivalent to saying that we are going to consider the analog frequencies. Remember that omega, the discrete frequency, is the analog frequency times ts. This is therefore equivalent of considering analog frequencies in the interval minus pi over ts, pi over ts, and this is, well, minus the Nyquist frequency, Remember that when we sample the signal, we assume that we have kind of removed all components above the Nyquist frequency. Okay, so therefore, if we obey the Nyquist theorem for sampling, well, we can simply consider the frequencies in this interval. The DTFT, well, produces something that is a complex number, so we can look at the magnitude and we can look at the phase. So this will yield a magnitude spectrum and a phase spectrum. The magnitude spectrum is even. It's an even function of the discrete frequency, and the phase spectrum is an odd function of omega. This should not come as a surprise, because remember that the DTFT, well, comes from the Fourier transform. It's obtained by sampling the Fourier transform, and the Fourier transform comes from the Fourier series, and we had seen that this Fourier series had similar properties. So let us have a look at the interpretation of this discrete frequency, and we have already seen something over here. Well, remember that omega n is pi over ts, right? So ts is pi over omega n. So if you inject that in here, you have the relation that is over here. So this is something that can be obtained quite easily. So since we are having a magnitude spectrum that is even and a phase spectrum that is odd, well, instead of looking the interval minus pi pi, we'll simply look at the interval 0 pi. Well, obviously from this relation over here, a discrete frequency of 0 will correspond to a analog frequency at 0, and here we see that a discrete frequency at pi will correspond to a analog frequency that is precisely the Nyquist frequency. As you might have noticed, we've skipped a few slides, and they concern an example of the computation of a discrete time Fourier transform. These slides are there for your information, so you can have a look at it if you want to. Well, this is a slide that summarizes what we've seen so far, and this slide can also help you to obtain each of the transforms that we have seen in the course. If you start, for instance, from the Laplace transform, it is quite easy to obtain the Fourier transform, the Z transform, and the discrete time Fourier transform. So as I've said previously, this discrete time Fourier transform is not very useful because it's only discrete in time. We want something that is also discrete in frequency so that we can start working with it on a processor, and this is what we'll see in the next slide. So in the next slide, we're only going to keep the bottom part of the slide, so the Z transform and the discrete time Fourier transform. So here above on the top right, you see the discrete time Fourier transform that we have obtained at the beginning of this section. That was not very useful because omega here is a continuous variable, and remember that this DTFT is periodic of period 2 pi. So what we'll do is, of course, consider this discrete time Fourier transform over the period 2 pi, and what we'll do is sample the discrete frequency, and we'll sample it like this. Okay, so L will be a variable, and n here will be the sample index, and you can see here that little n, the sample index, goes from 0 to L minus 1. Why L minus 1 and not L? Well, because you see, if you take L over here, you obtain 2 pi, and well, this is equivalent to the discrete frequency 0. Okay, so the index n goes from 0 to L minus 1. Very often we're given a sequence, okay, where the index k is going from k is equal to 0 to n minus 1. So we're given n data points. Okay, so sampling the discrete frequency as we have done over here is equivalent of saying that the equivalent analog frequency will be as shown over here. This is simply obtained by this relation over here. Since omega n is 2 pi n over L, well, and this is our frequency, our analog frequency will be omega n divided by Ts, so this will be 2 times pi Ts n over L. Okay, and this is omega n. This is how we obtain this relation over here. And you can see that if you plug this relation here in the discrete time Fourier transform, and since we are only considering sequences of n data, well, the discrete time Fourier transform becomes also discrete in the discrete frequency. So we talk about simply the discrete Fourier transform. It's discrete in time and in frequency. So you can see that you can very simply obtain it from the discrete time Fourier transform, which you can very simply obtain from the Fourier transform. Okay. Well, what can we say? Well, usually we consider omega in the interval 0 pi. Why? Because the magnitude spectrum is even and the phase spectrum is odd, so it makes no sense to consider it in the interval minus pi pi, right? So if we look at it, well, the interval 0 pi corresponds to the interval for the index n that goes from 0 up to L over 2. Okay, and if you put L over 2 in here, this corresponds for the analog frequency to the interval 0 to the Nyquist frequency. This will be very important once you start working with the DFT. It will produce a sequence of complex numbers, and if you want to construct, for instance, the amplitude spectrum, you have to transform this n into a frequency, and this can be done using this relation over here. Well, the DFT, the discrete Fourier transform, is obtained from the discrete time Fourier transform by simply sampling the discrete frequency as follows. And you should always be suspicious when you sample something. Remember, and this is covered by the section dedicated on the sampling theorem, that if we sample a continuous signal over time, okay, what will happen in the frequency domain is that the spectrum becomes periodic, right? And what you can show, we will not show this, is that by time frequency duality, sampling a spectrum over frequency, right? This is what we're doing when we go from the DTFT, the discrete time Fourier transform, to the DFT. We sample over frequency. What will happen is that if you look at the equivalent time signal, well, the equivalent time signal will become periodic. So here's what happens if, well, the continuous function is sampled in the time domain, and we'll see that there will be periodicity in the frequency domain. So here we're given this continuous time function f of t in blue. Its spectrum is shown here in green, so it's the amplitude spectrum, and well, we assume that this amplitude spectrum is band limited. Then we sample the signal, and you remember that we do this using the Dirac comb, and we obtain here the sampled signal. And if you take the Fourier transform of this sampled signal, you can see here that the spectrum becomes periodic. And well, if Ts meets the Nyquist condition, there will be no overlaps in the motifs that you see here in blue. If the Nyquist condition is not met, the motifs will overlap, and this is called frequency aliasing or frequency folding. Well, in our situation here, our new situation, we will not do sampling in the time domain, we'll do sampling in the frequency domain. So what will happen is not frequency aliasing, but time aliasing. So this is the situation. We're given here a sequence of n numbers, right? And outside this support 0 n minus 1, the function is 0. So what you can do is compute the discrete time Fourier transform, and this will yield, in this case, an amplitude spectrum that we will consider in the interval 0 pi, and this amplitude spectrum is continuous, right? So what we'll do if we go to the DFT, we'll sample this discrete frequency capital omega as shown over here, and this will lead to the DFT. And as you can see here at the bottom right, the amplitude spectrum becomes, well, discrete, obviously, because we have sampled the discrete frequency capital omega. So what is the influence of that? Well, the influence of that is that if you would take the inverse DFT, what would result is a time signal f tilde that is the repetition of the original signal f of k. And well, you see that this signal is repeated every L. Okay, so you take the motive and then you shift it by ml, and this is how you obtain this f tilde. But what is important is that f tilde is now periodic, and what could happen if L is not chosen correctly is that you have superposition of the motives in F tilde, and this will be time aliasing. Well, in our case, you can see here that n is equal to 5. Indeed, we have 5 data points from 0 to n minus 1. And L is equal to 6. 0, 1, 2, 3. 3 corresponds to L over 2, so indeed L over 6. And you can see that, well, you have a repetition of the original signal every 6. So you can see here already that in order not to have any time aliasing, you will need L larger or equal to n. So what we have seen so far, we have obtained the discrete Fourier transform from the discrete time Fourier transform by sampling the discrete frequency as follows. We knew already from previous sections that sampling in the continuous time case yields a periodic spectrum over frequency, and we have just seen that, well, when we sample over frequency, as is done over here, what will be obtained is a periodic time sequence by the inverse discrete Fourier transform, and this is what is shown over here. So it's the original signal that is shifted by L, and all these different contributions are then added to obtain a, well, periodic time sequence. This has not been shown mathematically. In one of the slides that will follow and that I will skip, it is shown mathematically, so it's there for your information if you're interested. As mentioned, you can have time aliasing when this periodic time sequence is produced when L is smaller than n, okay, because there will be superposition of shifted versions of the original sequence f of k, and this is called time aliasing, and you can see it as the dual of frequency aliasing that occurs when you sample with respect to the time variable. So this is the example that we had considered previously, and remember here that we have n is equal to 5. We are n data points in the original sequence, and L, the number of points that we take to, well, obtain a discrete variable omega, is L is equal to 6, and you can see that it is equivalent to taking an original sequence with 6 points, where at the end we have added a 0, and this is called zero padding. Okay, so taking L larger than n corresponds to taking an equivalent sequence where you had the n data points and you have added L minus n zeros at the end, and again this is called zero padding. This is the case where L is equal to n, and you can see that the function f tilde is periodic, and it's simply constructed from the original sequence that are, well, shifted by multiples of the length of the sequence over here. So you can see here that there is no zero padding, right? But still we don't have any time aliasing. This is why, well, you often obtain the formulas of the DFT in the literature with L is equal to n. Well, here you have a case where L is smaller than n. Okay, L is equal to 4, where you have 5 data, and of course if you repeat this section every 4 and you add, well, you will have indeed superposition of the motive and you will have time aliasing. So it is clear that L should be larger or equal to n. Okay, and taking L larger than n will involve zero padding. We have seen that you can choose L larger than n, and in practice this will result in zero padding. So the question is, why would you do this? Well, the first thing that you have to know is that you can only do this if the sequence is aperiodic, because otherwise you'll have a strange phenomenon that is called spectral leakage that will appear. Well, a first reason why you can choose L larger than n is because your n, and the number of data points, is small. So if you compute the DFT, you'll have a small number of points in your spectrum, so the spectral resolution will be poor. So what you can do is increase L to have a better spectral resolution, and as we have seen, you can do this by adding a number of zeros, L minus n zeros, at the end of the sequence. This is called zero padding. Another reason why you can do zero padding is because when you use the FFT, and this is what we'll do, we'll see that the FFT is the fast Fourier transform, an efficient implementation of the DFT. You need a number of data points that is a power of 2. So you need to write n as 2 to the power alpha, where alpha is some integer. In some cases, well, the number of data that you've got is not a power of 2. So what you can do is add a number of zeros at the end, so that the length of your sequence becomes a power of 2, and that you can use this FFT. But remember, you can do this trick only for aperiodic signals. Well, when your signal has period np, right, and we have a length that corresponds to a multiple of np, so we'll write it as capital K times np. Well, if you do zero padding, you'll destroy the periodicity. So this is something that you should not do. Remember that if your original signal is of period t, you should choose ts as t divided by some integer, and here we've called it np. If you do not do this, your original periodic signal might become aperiodic when it is discretized, or it can become also periodic but with the wrong periodicity. So if you have a signal of period t, please sample your signal such that you have an integer number of samples in one period. This is something that we have considered when we were talking about sampling of periodic signals in section 7. In practice, of course, we can only measure a signal over a limited time span, so that we obtain n data points where n is finite. We've seen that in theory the DFT, the Discrete Fourier Transform, will presuppose that the measured signal is repeating itself. So it is assumed that what you measure is the repetition of one or several periods of a periodic signal. In practice, well, the measured signals will not be periodic, and the DFT will see the data as a repeating sequence, and it will kind of see discontinuities between the ends and the beginnings of the sequences. These discontinuities will be seen as, well, spurious frequencies or spectral leakage. And of course, these spurious frequencies do not really exist in the original signal. What you see here is a case with no spectral leakage. The original continuous time signal, which is periodic, has been sampled such that the period corresponds to 8 points, and as you can see, well, we have considered two periods over here. So if you take the discrete Fourier transform of that signal, there will be no spectral leakage, because you know that in the background this f tilde here that has been reconstructed from shifted versions of the original fk will represent the original signal that was continuous time in a good way, in the sense that the periodicity is the same and there are no discontinuities. So in this case you should not expect spurious frequencies in the discrete Fourier transform spectrum. In this case, the underlying continuous time periodic signal has not been sampled properly and there will be spectral leakage. Remember that there should be an integer number of times the sampling period in one period of the original periodic signal. This is not the case right here. As a result, the discrete Fourier transform of this signal will present spectral leakage, as the underlying periodic signal f tilde does not represent the continuous time periodic signal well. The periodicity is wrong and you can see that there are discontinuities. Well, we can see that sometimes there is spectral leakage. There are frequencies that do not really exist that pop up in the spectrum. One way you can deal with this is to select large n, and this will attenuate the effects of spectral leakage. Another thing that you could do is windowing, and this will make sure that the ends of the segments will go to 0 or to small values so that they connect from beginning to end. But of course this will lead to a compromise between reducing spectral leakage and smearing the spectrum, because you will be changing the spectrum since you will be changing the original signal. Before you do windowing, of course, you should do everything that is possible to decrease spectral leakage as much as possible. For instance, if you have a periodic signal, you should do your sampling in a smart way. This means that you need to have an integer number of samples in one period. If you do things correctly on a periodic signal, there is no reason why you would have spectral leakage. But if somehow you get data where there is danger of spectral leakage, well, windowing can offer a solution. Well, here we have a few examples of window functions that are available. Those of you that will follow the Matlab sessions will explore this, and it's also explored further down in the course with an example of windowing. So here is an application of windowing. So you see the signal before windowing, that's the dotted line, and it's also showing that, well, this is indeed a sampled signal, and you can see here that there is a discontinuity. At the beginning you have a 0, and at the end of the sequence, well, you have a 1. So if you take the discrete Fourier transform, remember that in the background it's as if you have this signal repeating itself, so you will have a discontinuity from 0 to 1. And the idea is that, well, you can use windowing to bring the beginning of the sequence and the end of the sequence to 0 or a very small value, so that now if you take the discrete Fourier transform, these motives will adjust. When you put them one after the other, there will be no discontinuity. Of course, there will be no spectral leakage, but you can imagine that since you have kind of changed the signal, this will also smear the spectral content. So there is a trade-off here. So from what we have seen in the previous slide, we see that the discrete Fourier transform of a signal of length n can be obtained as follows. Here n is the index that will be used for k and for n. So both k and n range from 0 to n minus 1 if we are taking the assumption here that L is equal to n. There is of course an inverse discrete Fourier transform, and it looks a lot like the discrete Fourier transform. What are the differences? Well, here the sum ranges over n, whereas there it ranges over k. Of course, f of n, well, the result of the Fourier transform, takes the place of the signal f of k, and we have here a plus instead of a minus. Okay, notice also the presence of this factor 1 over n, and note that both the Fourier transform and the original signal are assumed to be periodic of period n. So if we want to reconstruct the signal from the discrete Fourier transform, we have to use this factor 1 over n. You can see that f of k, the original sequence, is decomposed in complex exponentials of discrete frequencies 2 pi n over n, and the contributions at these frequencies will be fn over the number of data. So this is why when we represent the spectrum, we'll do it after normalization by a factor that is 1 over n. Well, we have seen that if we start from a sequence f of k where k ranges from 0 to n minus 1, so we're given n data points, we can produce a sequence of complex numbers f of n, and here the index n will range from 0 to n minus 1. So we'll assume that here that L is equal to n, right? So why do we range from n 0 to n minus 1 and not n? So because if you put n in here, you would have 2 pi, and 2 pi is the same frequency as the frequency 0, right? Remember that from this complex sequence, well, we can obtain the magnitude spectrum, and in most cases it's only the magnitude spectrum that will be represented. Well, it will be indexed by n, but n is not very interested. We would like to relate this n to frequencies. We've seen previously that if n ranges from 0 to n over 2, the number of data over 2, then we can see that the discrete frequency that has been sampled, it's expressed here in radians, ranges from 0 to pi. We remember that the discrete frequency is the analog frequency times Ts. We are interested in the analog frequency, so the analog frequency will also be indexed by this n, and it will range from 0 to pi over Ts. This is the same thing as from 0 to the Nyquist frequency. And if you want to work with a frequency expressed in Hertz, then you can do something similar, and this quantity here, when indexed by n, will range from 0 to the Nyquist frequency, and the Nyquist frequency is 0, the sampling frequency divided by 2. So this is how you can make the link between the indexed n and frequency in your amplitude spectrum. So instead of considering omega in the interval 0 to pi, what you can do is consider it in shifted periods, for instance the period from minus pi to pi, and this can be done using the Matlab command, for example, FFT shift, fast Fourier transform shift. We'll talk about the fast Fourier transform later. And this command shifts the zero frequency component to the center of the spectrum, as we will see. So let us take an example. We'll take a sine signal, sinusoid, right, of amplitude 1. It will be sampled at 100 Hertz, so 100 samples per second. We'll take 1024 points. 1024 is a power of 2. We will see later when we talk about the FFT that this is important. We'll take 10 periods of the signal and we compute the period of the sine in such a way that we start with 0 for the first sample and that the last sample is such that the next sample, the one that would follow, is again 0. We do this to prevent spectral leakage. We want that when we take this vector here and we repeat it, well, we want continuity to prevent this spectral leakage. Note that the period of the sine will be slightly over 1 second. To be exact, it is 1.024 seconds. So of course the frequency of the sine, 1 over the period, will be slightly lower than 1 Hertz. So here is the sinusoidal signal. You can indeed see that we cover 10 periods. Notice that this signal is indeed discrete, but this is not visible because we have chosen a sampling frequency of 100 Hertz. You can see that if you repeat this signal, you will have continuity because the next sample, if you repeat it, will be 0 and we will keep the periodicity. If you let the signal start at 0 and finish at 0, then you'll have 0 and a 0 again, and you'll have a little bit of spectral leakage. We can now compute the DFT, and to compute the DFT we'll use the command FFT. We'll see later in the course that the FFT is an efficient algorithm to implement the DFT. Right, so what will come out over here is a vector Fn as defined previously. Well, it's always a good idea to remember what this means. Remember that starting from the Fourier transform and then discretizing, we have obtained the DTFT, and there the variable was omega that lives in the interval 0 to pi. We do not consider 2 pi again, otherwise this would lead to the same discrete frequency. And remember that omega was omega ts, right? Then we have considered the DFT and we have said, well, this is not really useful if we want to work with a processor. This is a continuous value, we'll discretize it, and we have written omega n is equal to 2 pi n over n, and here n is in the interval, well, 0 of course, up to n minus 1, right? N minus 1, because if we take n, we have again 2 pi, and this is the same frequency as 0. So of course you would like to write this in terms of this frequency here in radians per second. So omega n here is 2 pi over ts n, small n, the index, over n, the number of data, and then the frequency in hertz. We have 1 over ts, so that's the sampling frequency, divided by n times the index n, right? So this thing here is the spectral resolution, right? So what we'll do now is use the command FFT shift, and this command will rearrange the outputs by moving the zero frequency to the center of the axis. So instead of having the n like this, what we'll have is n in the range minus n over 2, right, up to n over 2. But if you take n over 2, it's the same as here. We'll have the same frequency as here, so we'll go to n minus 2 minus 1, right? This is what we'll have after this, well, shifting operation. And again, well, the frequencies can be constructed as the spectral resolution fs divided by n times this index, now this index over here. And indeed, you can see that this is how we construct the frequencies. Of course, what we have to do is to take the absolute value, because we want the amplitude. This is the modulus, right? This is a complex number. And then we multiply by 1 over n for the normalization. When I speak about n over here, it's of course the n that has been used here in the FFT command. We have called it here in the Matlab code nFFT. Then you have your frequency vector. Well, you have your vector with the amplitude spectrum, so everything is ready for plotting. And instead of using the plot command, what is often done is to use a bar graph, so you use the bar command, or you can also use the stem command. In this plot, we expect a spectrum that is in between minus fs over 2 and fs over 2, so minus 50 hertz and 50 hertz. Since we expect to see, well, spectral lines around minus 1 hertz and 1 hertz, we have zoomed in the interval minus 5. So this is the spectrum that you obtain. You see a spectral line at 1 hertz and one at minus 1 hertz, and you can kind of see here that the amplitude is, well, 0.5, whereas our original signal, which was y of t is equal to sine 2 pi t over t, had an amplitude of 1. So here in this case, t is approximately 1 second, right? So the frequency of the sine is approximately 1 hertz, and this is indeed the frequency that you see, right? So why do we see also a contribution, a spectral line at minus 1 hertz? Well, this should ring a bell, and this is something that we have seen referred to the animation, where we have, well, constructed a sine or a cosine using two phasors turning in counterclockwise direction and in clockwise direction. Indeed, we know from the Euler identity that we can write this sine as the exponential of j2 pi over the period t minus the same exponential but with a minus sign over here, divided by 2j, right? This is a phasor here that is turning counterclockwise, and this one is turning clockwise, right? So here 2 pi over t is the frequency that you see over here, right? 2 pi over t, and this one here is turning clockwise. We have the minus sign, so this frequency corresponds to minus 2 pi over t, and we have a factor here 1 over 2. So if we take the modules, this one will be left, and this explains the 0.5 that you see over here, right? So notice that we have, of course, because it's an amplitude spectrum that is even. So we have a mirroring effect if you do this with respect to the zero frequency. So usually what we'll do is use discrete frequencies in the interval 0 pi, and we'll use the indices n, small n, ranging from 0 to n, the number of data, divided by 2, right? So we'll only use, well, in this case here, this part of the amplitude spectrum. And since we have here an amplitude 1 in this spectrum that will only consider positive frequencies, what we would like is to have, well, the original amplitude. So what we'll do is multiply here the spectrum by a factor 2, so that we have here a spectral line of amplitude 1. We'll just have to pay attention at what happens at the zero frequency, because there you should not multiply by 2. Well, we have seen that for a sinusoidal signal, we see two purely imaginary complex exponentials of half the amplitude, and in the resulting spectrum we see two spikes, one at the original frequency and one at the mirrored frequency, right? If we want to retrieve the amplitude of the original signal, what we'll do is work only with the indices that go from 0 to n over 2, right? So this is considering the spectrum in the interval 0 pi. We can do this because the amplitude and phase spectra are respectively even and odd. Okay, so it does not bring anything to consider the discrete frequency in the interval minus pi pi. So we'll work in the interval 0 pi for the discrete frequencies, and for the indices for 0 from 0 to n over 2. And since we want to recover the amplitude of the original signal, we do not have to normalize by 1 over n, but by 2 over n, right? There is one frequency where we don't have to do this multiplication by 2. It's the zero frequency. It's the frequency that corresponds to n is equal to 0. This is the way the amplitude spectrum is usually computed in Matlab. We use the FFT command to implement the DFT efficiently, right? And we obtain a vector Fn, right? So in this case we'll use the index n in the interval 0 up to n over 2. Remember that we have discretized the discrete frequency as follows. It's 2 pi n over n, where n here is in this range. This means that this is in radians. If we consider the frequency in radians per second, this will be, you have to divide by ts, 2 pi over ts n over n, and of course we are interested in the frequency in hertz, right? And this will be 1 over ts, so that's the sampling frequency, divided by n, and here we have the spectral resolution times n, right? So here we have it, n ranging from 0 to n over 2. Again, n here is n that is used in the FFT command, so here n FFT times the spectral resolution. So this is okay. We have our frequency vector. Now we have to take the first n over 2 values in the vector x. But here n ranges from 0 to n over 2. In Matlab, well, the indices range, well, they start from 1. So of course we have to start from 1 and go to n over 2 plus 1, right? Then we have to take the module, because these are complex numbers, right? And as we have said, we have to, well, normalize by 2 over n, the one used in the FFT command. And then what we have done is normalized also the DC component, and it should not be normalized. So we take the first element in the vector over here and we divide it by 2. So now everything is ready. We have the frequency vector, we have here the vector with the amplitude spectrum, and we can plot it as usual using, for instance, the bar command or the stem command. In this case here, fs is equal to 100 Hertz, right? So we can look at the spectrum up to fn and the Nyquist frequency, which is 50 Hertz, but we have, well, limited the spectrum to 10 Hertz because we expect now a ray, a spectral line at the 1 Hertz, and since we have normalized by 2 over n, we should see a spectral line of amplitude 1. And in this spectrum we see what is to be expected, right? So the amplitude of the spectral line is 1, and the spectral line is very close to the frequency of 1 Hertz, which is precisely the frequency of the sine that we have considered. Remember here that we only see the interval 0 to 10, but with a, well, sampling frequency of 100 Hertz, you can look in the frequencies up to half the sampling frequency, so up to the Nyquist frequency. We have decided here to zoom in on this range. Well, let us run this code and have a look at the results in Matlab. So we'll first generate the data, right? So this is the plot. Now we can have a look at this spectrum, and it's this symmetric spectrum, right, that ranges from minus 50 Hertz and 50 Hertz, but that we have, well, zoomed in at in the range minus 5. So we can have a look at the frequencies where the amplitude spectrum is larger than 0.1. We find 2 frequencies. If we look at these frequencies, they correspond to, well, something that is close to 1 as expected, and we can now compare this to the, well, frequency of the sine, and you can see that this is exactly the same. So we have really pinpointed the frequency of the sine, and we can now look at this spectrum over here. So with only positive frequencies, again, we can find the frequencies where the amplitude spectrum is larger than 0.1, so there is only 1, and of course it corresponds to the same frequency. So in summary, we consider the indices from 0 to n over 2. Okay, this is what you see over here. N ranges in the interval 0 n over 2, and you go in steps of 1 since n is an integer, and the corresponding interval for the frequency is in the interval 0 to fn, right? And of course here you'll go by steps of, well, it's easy, fs over 2 divided by n over 2. So this is fs over n, right? So another way to see this is that the indices that range from 0 to n over 2 correspond to frequencies that are fn times the index n divided by n over 2. So n is equal to 0 corresponds to the frequency 0, and n over 2 corresponds to the Nyquist frequency. This here is the spectral resolution, and you can rewrite it as 1 over Ts times n, and this is the duration of the experiment, right? So the spectral resolution, what you've got over here, is inversely proportional to the duration of the experiment. Notice also, and we've seen that in the previous example, that the highest frequency that is present in the spectrum is of course the Nyquist frequency, which is, well, the sampling frequency divided by 2. So what we'll do here is take an example and, well, illustrate the concepts of spectral leakage and windowing. So what we have is an example that looks a lot like what we have done before, right? But in test number 1, we'll have exactly the same thing as what we have done before. So we consider a periodic signal and we consider exactly 10 periods. There will be no windowing, and the number of elements used in the FFT is equal to the number of points. So this NFFT here can be seen as the L in the course. So in test number 2, we'll do exactly the same, but we'll choose the number of points used in the FFT as 2n. So we'll choose L is equal to 2n. So this means that we add n zeros at the end of the sequence. There will be no windowing. In test number 3, what we'll do is we'll consider 10 periods and a quarter. So this will lead to a sequence where the beginning and the end of the sequence will be at different values. So this will lead to spectral leakage. And test number 4 is exactly the same test as test number 3, but in test number 3 we do not do any windowing, and in test number 4 we'll do windowing to kind of attenuate the effects of the spectral leakage. This is the rest of the code. This is the generation of the amplitude 1 sinusoid with a frequency approximately 1 Hertz. Here is the code to generate the amplitude spectrum as discussed before. If there is windowing, the Anning function is used, and for test 2 we're doing a zero padding, as you can see over here. So a data set only composed of zeros is added at the end of the data set, the original data set, and then what is done is to plot the signal and to represent the amplitude spectrum, and as usual we'll do this with the bar function. This is the signal from test 1. This is a signal that we've seen before, and it has been constructed in such a way that the signal starts from 0, and here the last sample is such that the next one would be this sample that corresponds to 0. Remember that in the background, when you compute the DFT, the assumption that is made is that the signal that you're analyzing will be repeating itself. So if you repeat this signal, well, it will start at 0. You will not have here a discontinuity, so you will have no spectral leakage. And indeed, because we have taken our precautions when we have sampled the sinusoid, we do not have any spectral leakage visible. We have a nice clean spectral line at 1 Hertz at the amplitude that is expected, that is 1. Well, this is the signal from test 2, and we can see that it's the signal from test 1 where we have added n zeros, and the presence of these zeros is going to destroy the periodicity, as you can see. This is the spectrum from this signal generated by test 2, and obviously the spectrum is not representative of the original signal, so you can use zero padding but not for periodic signals, as this zero padding will be interpreted as multiplication by a rectangular window, and as you know, a rectangular window is seen as a cardinal sign in the frequency domain, and this is what you see over here. This is the signal that is obtained from the third test, and as you can see, we consider here 10 periods and a quarter of the signal. And remember that if you take the discrete Fourier transform, well, this is going to be seen as the discrete Fourier transform of this signal that is, well, repeating itself indefinitely, and this will cause, well, discontinuities, because you'll have discontinuities that go from 0 to 1, and this will lead, of course, to spurious frequencies appearing in the amplitude spectrum. This is indeed what you can see in the amplitude spectrum of the third signal. You can see a spike at 1 Hz, but you see also the presence of these spurious frequencies that have appeared. Well, the signal here that you see has been obtained from the signal from test 3 after applying windowing, and now you see here that this sequence will start and end at 0, so there will be no spectral leakage, but of course the signal has been modified. Well, this is the amplitude spectrum of this fourth signal. You can see that the windowing has decreased the influence of the spurious frequencies, but you can also see that the spectrum is smeared around 1, so there is a spread of frequencies around 1, and you don't see a clear spike at 1 Hz. So the conclusion is, if you're working with a periodic signal, you should do the sampling in a correct way. This means that 1 period of the signal should correspond to a number of times, an integer number of times, the sampling period. If you do that, well, you won't have any problems with spectral leakage, and there will be no need for windowing. Another conclusion that we can draw is that zero padding is, of course, a very bad idea when you want to compute the amplitude spectrum of a periodic signal. So let us make a summary of all the Fourier series and transforms that we have seen in this course. We've started with the Fourier series, and this is applicable to continuous time periodic signals, and the resulting spectrum is discrete. It's either an amplitude or phase line spectrum. Then we have seen that in the limit, if you consider signals that are periodic and you let the period go to infinity, you obtain an aperiodic continuous time signal, and this Fourier series becomes the Fourier transform, and the resulting spectrum is now continuous. Okay, except of course if you take a periodic signal, then the Fourier transform will still be discrete. For instance, if you take the Fourier transform, of course, of a sine, then of course you'll have only a spike at the frequencies omega 0 and minus omega 0. What we've done in this section is, well, discretize time, and we obtained the discrete time Fourier transform applicable to discrete time signals, but the spectrum, the variable frequency, is still continuous, and of course the spectrum becomes periodic. This is because we sample, right? This is a result of the sampling theorem, and what we have done next is of course sample or discretize the variable frequency, and then we obtain the discrete Fourier transform, which is discrete in time and frequency, so the spectrum is discrete and periodic. In this subsection we talk about the fast Fourier transform. It's an invention that is credited to Cooley and Tuckey, two engineers that published an article concerning this fast Fourier transform in 1965. The work on the fast algorithms concerning the DFT can be traced back to Gauss's work in 1805, but the authors of the article, so Cooley and Tuckey, realized that Gauss's method could be implemented efficiently with computers. So the FFT, even if it contains the word transform, is not a new transform, but rather an efficient implementation of the DFT. It can also be implemented or used to compute the inverse DFT, because we've seen that the DFT and its inverse are very close. It involves a change of sign and this normalization. We have seen that the discrete time Fourier transform is difficult to implement on a processor, and this is why we have discretized the variable frequency, this discrete frequency, and as a result we have obtained a DFT that can be easily implemented on a processor because both time and frequency are discrete. If you try to implement the DFT based on its definition, you will see that it is not very efficient because you do not use all the symmetry properties of the DFT, and when you evaluate the DFT, you will see that this involves n-square complex multiplications, where n, of course, is the number of data points in your DFT. The FFT is an efficient implementation of the DFT that uses the symmetries, but to use the symmetries you have to impose that n is a power of 2, where alpha is an integer. And when n is a power of 2, the number of complex multiplication decreases from n squared to n log n, and it's the logarithm is here in logarithm in base 2. So there is a gain in complexity of n squared divided by n log n. So the gain of complexity is n divided by log n. If we take a value of n is 1024, which is not a number of data points that is very high, in applications you go much higher than 1024. Well, for this n is equal to 1024, you see that the gain in efficiency in using the fast Fourier transform is already around 100. So this is why in practice it's always the fast Fourier transform algorithm that is used to efficiently implement the discrete Fourier transform. Applications of the FFT used to compute the DFT are first of all spectral analysis, looking at the frequency content of discrete time signals. Then you can use it also to compute the convolution of time sequences h of k and x of k, respectively of length m and k. You know that the convolution of h and x will have support m plus k minus 1, so you'll have to add a number of zeros in the sequences of h and x before you take the convolution. And since we're going to use the FFT, it's good to have a number of data points in h and x that is a power of 2. So the idea is that you can go to the frequency domain by taking the DFT, and then in the frequency domain taking making a convolution is very simple because it's simply a product. And once you have the product, you have the spectrum of the convolution signal yk, then you can take the inverse DFT. Another application is denoising. If you go to the frequency domain, noise can often be detected and removed more easily, so it allows you to reconstruct a signal with smaller influences of the noise. As you have noticed, I've skipped quite a few slides. These slides have to do with the implementation of the FFT algorithm, and these slides are there for your information only. The following code has to do with a denoising application. So what we'll do is emulate a noisy sinusoid and analyze it in frequency by looking at the amplitude spectrum. So this part of the code is really constructing this noisy sinusoid. This signal has two components. This one over here, ys, and you can see that ys is the sum of a 50 Hz sinusoid and a 120 Hz sinusoid, right? And the 50 Hz sinusoid has an amplitude of 0.7 and the 120 Hz sinusoid an amplitude of 1. And then a random number or random noise is generated, and this random noise is added on top of this sum of two sinusoids. And of course you'll have the possibility to look at the resulting signal, and you will see that it's difficult to see in the time domain that this signal has an underlying sum of two sinusoids in the background. So what is done over here is the code that you should recognize by now to compute the amplitude spectrum, and then the amplitude spectrum is presented. So here at the top left you see in green the original signal without the noise. So when you look at that signal, you can imagine that it is indeed the sum of two sines. But if you're given the blue signal, which is the green signal with this random noise added to it, well, it's difficult to imagine that it's the sum of two sines. But if you go to the frequency domain, and what you see here is f of n. Okay, so it's the raw data that is produced by the FFT, and we take the amplitude. Okay, so we have here 1024 points, and you see what happens. So if you look at it with the index n, well, this is not really something that you can use for interpretation. So what is done is that only the first n over 2 points are taken, right? And here you see everything with respect to a normalized frequency. This 1 here means that this is the Nyquist frequency. In our case, the Nyquist frequency is, well, fs divided by 2, so it's 1000 divided by 2. So if you look at the spectrum, okay, so here it's a spectrum with a variable that is the normalized frequency, and here you see directly the frequency in hertz. You can clearly see the white noise. So white noise is actually noise that is evenly distributed over all frequencies, and you can see the spikes at the frequencies of 50 Hz and 120 Hz. Here the amplitude is 1 in the original signal. It's not exactly 1 in the spectrum, because of course you have the influence of noise and the fact that you only have 1024 data. Here again the amplitude is 0.7, but again, because of this noise and this finite amount of data, you don't get the amplitude 100% correct, but at least here you see clearly the presence of these two sines at the frequency 50 and 120 Hz. So here we have two signals, x and y. These signals have finite support. They have both support 4. So at index k is equal to 0, you have a 1 here, k is equal to 1 minus 3, and so on. And well, outside this indices from 0 to 3, the whole signal is 0. And similarly here you have here a signal y. And what we want to do is to take the convolution of these two sequences. We know that the product, okay, the convolution sum, sometimes called product also, is, well, will have length, the length of the support of x plus the length of the support of y. So 4 plus 4 minus 1, so it will be 7. So what we'll do is add here 3 zeros, 3 samples, and what we'll do is take the FFT. So we'll take the DFT, we'll go to the frequency domain, and we'll use 8 samples because 8 is the power of 2, right? And now we obtain the DFT of those two signals. In the frequency domain, convolution becomes a product, so we have now the DFT of the convolution of x and y, and what you can do now is do the inverse Fourier transform. So here are those two sequences, xk and yk. So the DFT is taken, so this is what you will obtain, xn and hn. And then, well, of course, these T sequences are sequences of complex numbers. What you can do in the frequency domain, well, this convolution simply becomes a point multiplication. We do this, and then we do the inverse DFT, and this is what you obtain. If you want to check this by hand, you could do this by simply taking the Z transform of this one, so xz, and this is quite simple. It's 1 minus 3 z minus 1 plus z minus 2 plus 5 z minus 3. H of z will be 4 plus 3z minus 1 plus 2z minus 2 plus z minus 3, right? And then y of z will be the product h of z x of z, and then you'll do the inverse z transform and you'll obtain y of k, and this should correspond with what you've got over here. I have skipped a few other Matlab examples that correspond to, well, spectral analysis and, well, also zero padding. I will not spend time on this section here, getting started with Matlab or Octave. All these slides are there for your information, and for those of you that will have separate Matlab sessions, again, at least the third or the fourth time, please attend those sessions and participate actively, because they will illustrate the course of signals and systems. Here an example with Python in the JupyterLab environment, itself in the Anaconda environment. In JupyterLab, well, you have an environment that looks a lot like the Matlab script environment. As I've said before, this is, well, something that is more and more used in industry. This is why I'm introducing it in the course, and all those examples in Matlab and JupyterLab will be put on the web page that is associated with this course. So this example looks a lot like the example that we've considered in Matlab with the denoising. So what we have here are two sines at different frequencies and amplitudes. They are given over here. So the frequency of this one is 50 Hertz and this one 80 Hertz, and we add random noise here, and the particularity is here that mu is equal to 1. So on average what is added here is 1 with a variance of 1. Okay, so we'll have here a DC component of 1. So this is the signal that is generated. You can see here that the average is indeed 1, and you cannot imagine here the presence of two signs. And then you can of course compute the amplitude spectrum using the command FFT. 2 over n is the normalization that we've considered. Remember that the zero frequency does not have to be multiplied by 2. Okay, so this is why we divide by 2 prior multiplication by 2 over n. Remember that in Python, well, we start the index at 0 and not at 1. And then of course you can plot the amplitude spectrum. Here it's an amplitude spectrum that goes up to the Nyquist frequency. The sampling frequency was 800, so half of that is 400, and we can clearly see the spikes. Okay, so here it's a zoom with a frequency that goes up to 100 Hertz, and we can see the component at DC, at the zero frequency, and we can see clearly the spikes at the frequencies of 50 Hertz and 80 Hertz. Well, this concludes this course on signals and systems. Do not hesitate to react by email to propose, well, changes, improvements, comments, and things like that. Thank you.